Hello everyone. In this video, we are going to be looking at Victor Meyer's experiment. Here, I'm going to be walking you through introduction to Victor Meyer's experiment, the assumptions stated by Victor Meyer during his experiment, relation between vapor density and molecular mass, important equations we often use in solving Meyer's experiment problems. Then we look at questions and answers that are related to Meyer's experiment. So let's get started. Now, the introductory part. Victor Meyer, in his experiment, was able to determine the vapor density of a gas by using relation derived from the assumptions made. The vapor density of a gas was obtained by the formula derived by Victor Meyer. The formula, which represents the relation, is given by relative vapor density is equals to 1/2 times relative molecular mass. This relation is derived from the assumptions that we are going to consider in this video. If you are able to get the molecular mass of the gas, we'll be able to obtain the vapor density of that gas, which is the main objective of the experiment. Like I said, this equation that we are seeing on the screen, which represents equation 1, can be obtained from the assumptions that was stated by Victor Meyer. And with the help of the equation that we're going to be looking at under important equations, we are going to be able to calculate the molecular mass of the gas. With the help of the molecular mass, we can get the vapor density of the gas. So, what are the assumptions stated during Victor Meyer's experiment? So, as we can see on the screen, these are the assumptions stated by Victor Meyer in his experiment. Hydrogen is assumed to be a standard molecule. So instead of using oxygen, nitrogen gas, chlorine gas, any other gas, he used hydrogen in his experiment to obtain the equation one we are seeing on the screen. Hydrogen is a diatomic molecule. As you all know, hydrogen is having H2, is a homonuclear molecule. Volume of all gases are measured at standard conditions. Our standard conditions here are the STP, that's the temperature and pressure. So he measured the volume of all gases by using standard temperature and using standard pressure. Avogadro's hypothesis was also assumed during the experiment. And what is Avogadro's hypothesis? Telling us that if the temperature and pressure remains constant, equal volume of all gases, they will contain the same number of molecules. That means if V1 is equals to V2, then we can say that number of molecules N1 equals to number of molecules 2. So these are the four major assumptions that were stated by Victor Meyer during his experiment, and we are going to make use of these four equations to derive equation 1. So we want to show the relation between the vapor density of a gas and the molecular mass of the gas. Before we start, we need to know what we mean by vapor density. The vapor density of a gas is defined as ratio of mass of a given volume of a gas to the mass of an equal volume of hydrogen gas. As we have said, let's look at the formula. That means our vapor density is going to be equals to mass of a given volume of gas to the mass of equal volume of hydrogen gas. So if that be the case, let's look at it from the perspective of Avogadro's hypothesis. Like we have said, we are going to be using all these four assumptions that we have to prove the equation. So mass of a given volume of gas, that means if the volume of the gas is 50 centimeter cube, we use the same volume for hydrogen gas. That means for hydrogen gas, it's also going to be 50 centimeter cube. That means N1 is going to be equal to N2. Number of molecules will be the same, provided that the volume of the gas are equal. So in that case, since we said we are dealing with equal volume of a particular gas to hydrogen gas, that means the number of molecules is the same. Then we can as well write it as saying vapor density of the gas is equals to mass of X molecules of gas over mass of X molecules of hydrogen gas. Why will we be able to write this way? Why is it that the volume has turned to molecules? Because we said the volume of the gas is the same as the volume of hydrogen gas, and if the volume of the gas are equal, that means the number of molecules will also be equal. That's to say that we have followed the fourth assumption, which says Avogadro's hypothesis is assumed. Now let's consider one molecule. Let's assume that the molecule involved is 1. That means vapor density is going to be equal to mass of one molecule of the gas involved. Gas can be any gas with respect to mass of one molecule of hydrogen gas. Yes. So now that we are considering the X molecule to be equal to 1, since we say we are going to have the same number of molecules for the two gases involved. Now the next thing is that we follow the other assumptions that says that hydrogen gas is diatomic in nature. That means one molecule of hydrogen gas is diatomic. That means it is formed by two atoms. That is H plus H. That's homonuclear molecule. Since it is diatomic in nature, that means it is formed by two atoms. Two atoms form one molecule of hydrogen gas. That means we are going to replace our value by saying vapor density is going to be equal to mass of one molecule of gas over mass of one molecule of hydrogen gas is formed by two atoms. That is to say, two atoms of hydrogen gas. Two atoms form one molecule. With respect to this, we can as well say that the mass of two atoms of hydrogen is going to give us, the mass of one atom is 1 multiplied by 2. That will give us 2 grams. So in short, our vapor density is going to be equal to mass of, okay, let's do it this way. We are going to be having 1 over 2, which is the two atoms. We go out, then be left with mass of one molecule of the gas. So in that case, because this one becomes 1, in that case, let's analyze our mass of one molecule of a gas. If you remember, we have said that molecular mass is defined as the mass of a molecule of a substance. Since the substance involved here is gas, so we can just say that molecular mass of the gas is defined as the mass of one molecule of the gas. So in short, our vapor density is going to be equal to 1 over 2. Everything that we have here represents the molecular mass, and also is mass of one molecule of a gas. So we are going to be left with molecular mass, and this is how we are able to obtain the expression that we have written in the before. So that is the relation between vapor density of the gas and its molecular mass. That means with respect to the molecular mass, that means if you're able to get the molecular mass of the gas, be able to obtain the vapor density. Now, how are we going to get the molecular mass of the gas? That is going to take us to the next subtopic for in this video. Let's look at it, which is the important equations that we make use of when solving Victor-Meyer's experiments problems. The first equation we make use of when solving Victor-Meyer's experiment problems is ideal gas equation, which states that PV is equals to nRT. This P represents the pressure of the gas, the volume of the volatile liquid used in the experiment, number of mole, R represents universal gas constant, and T represents temperature in Kelvin. How do we make use of this equation? We're going to talk about that in a few seconds. The second equation that is important in this topic is number of mole equals to mass over molar mass or molecular mass. Like we have said, once we're able to get the molecular mass of the gas, we can obtain the vapor density. That means the approach is to get the number of mole. After getting the number of mole, we can use this to get the molecular mass and solve for vapor density. Sometimes the question will only requires us to solve for the mass or the molecular mass without even solving for the vapor density. The third one is number of mole equals to number of entities over Avogadro's constant. That's the third equation. Here we can be asked to solve for the number of molecules that we are going to have during the experiment, or we can be asked to solve for the number of particles. So we still make use of the first equation to get the number of moles. Then from the number of moles, we can multiply the moles calculated with our Avogadro's constant and get the number of molecules or atoms or particles, which depends on the entities given or required to be solved in the question. Then the last equation is pressure of the gas is equal to pressure from the atmosphere minus pressure of water. That's saturated vapor pressure of water. How does this equation works? Sometimes we can be given the saturated vapor pressure of water. So if you are given the result of the fact that in the containing vessel we have pressure of the gas, then we have pressure of water, while pressure from the atmosphere, that's our atmospheric pressure that is being exerted on the containing vessel. So if you are given the pressure of the atmosphere, pressure of water, which is saturated vapor pressure of water, we are going to make use of this equation. Sometimes will not be given. So if you are not given the pressure of water, that means pressure of the gas is equal to pressure of the atmosphere in this case. So this equation 1 that we have the pressure, how do we make use of it? This pressure that we have in equation 1, if you are given the pressure of water, that's saturated vapor pressure of water, that means for us to get this P, which represents the pressure of the gas, is going to be atmospheric pressure given minus saturated vapor pressure of water at a particular temperature. But if it is not given, we are not to assume. If it is not given, that means this P that we have in equation 1, which represents the pressure of the gas, is also going to be the same as pressure of the atmosphere. So these are the equations that we make use of when solving Victor-Meyer's experiments problems. So the last part of this section of this video rather is to solve problems related to what we have been discussing so far. So let's start by looking at the first example. So let's look at this first example that says 0.625 gram of a volatile organic liquid displays 13.10 centimeter cube of air in a Victor Meyer's experiment at 20 degrees Celsius and 1.01 exponential 5 Newton per meter square pressure. Given the SVP of water at 20 degrees Celsius is 2.31 exponential 3 Newton per meter square. Determine the relative molecular mass of the compound. You can feel free to pause the video so as to try it. So let's get started. We are to write the parameters involved in this question. Given data 0.625 gram, that is the mass. The mass of the volatile organic liquid is 0.625 gram. We are also given the volume of air that was displaced as 13.1 centimeter cube. And the temperature here is given as 20 degrees Celsius. We convert it to Kelvin to be 293 in Kelvin. The pressure of atmosphere, which is PATM, is 1.01 exponential 5 Newton per meter square. Given that the SVP of water, that's P of water, to be 2.31 exponential 3 Newton per meter square. Since we are given and the unknown is relative molecular mass, since we are given the P of atmosphere and P of water, first thing is to get P of the gas, pressure of the gas. So we start from, let me change the ink, from P of gas relation, which is given as P of atmosphere, pressure of atmosphere minus pressure of water, is equation 1. So let's try to solve for this. That means P of gas is going to be, atmospheric pressure is 1.01 exponential 5 minus 2.31 exponential 3, and P of gas will give us 9.869 exponential 4 Newton per meter square. Now that I've gotten the pressure of the gas, the next thing is to work with the volume. Now let's quickly talk about the value of R, because we are going to make use of R. There are two major values that we use in explaining R. A, we have R to be equals to 8.314 Newton meter, which is also known as Joule per mole per Kelvin, and the B part is R equals to 0.0821 liter or dm cube atm per mole per Kelvin. So these are the two values of R. Whenever we are making use of these two values of R, there are some things we must understand. To make use of the first R, which is 8.314, our pressure must be in Newton per meter square or must be in Pascal. Then the volume must be in meter cube whenever we are making use of this, simply because in the unit for R, which is 8.314, it is having Newton and meter, while the temperature is in Kelvin. So for us to be able to make use of 8.314, we need to convert our pressure to Newton per meter square or Pascal. Then the volume must be in meter cube. If you are to make use of the second equation, that means, as you can see from here, ATM, that means the pressure must be in ATM, then volume will be in liter or dm cube, simply because 1 liter is same thing as 1 dm cube. So while making use of 0.0821, which is the second value of R, we have to put our pressure in ATM, or ATM rather, and the volume will be in liter or dm³. Sometimes it depends on our parameters. The pressure can be in Newton per meter square and the volume is in dm³. So we need to look for a way to convert. So you can check the other videos that we have talked about conversion process for how to convert from one unit to another unit. So if you want to convert, let's say we are given the pressure in ATM and we want to convert to Pascal or Newton per meter square, we should always remember the conversion factor for that is going to be 1 ATM is equals to 1.013 exponential 5 Newton per meter square or Pascal. And if you want to convert the volume from centimeter cube to dm cube, you can always do that by using the conversion process as well. So let's continue with the solution. Now that we have all the parameters, we start by saying using PV equals to nRT, equation 2. We are interested in getting value for n, so make n the formula. We have PV over RT, that's equation 3. Then we can solve for n to be pressure is 9.869, which is the pressure of the gas that have been obtained from pressure of the atmosphere and at saturated vapor pressure of water, times volume. The volume is in centimeter cube, so we need to convert it to to meter cube. If you want to convert the volume, which is given in 13.1 centimeter cube, which is this, we convert it to dm cube, we are going to be getting the volume to be 1.31 exponential minus 5 meter cube. So in that case, we can have volume to be 1.31 exponential minus 5 over our value for R. Since the volume is in meter cube and the pressure is in Newton per meter square, then the value for R we are going to make use of is the one of 8.314 times temperature is 293 in Kelvin. So the value for N is going to give us, now that we have gotten the value for N, we have to solve for molecular mass, since the question demands for us to evaluate the molecular mass. So we recall that N is equals to mass over molecular mass of the gas. So if we make molecular mass the sub formula, molecular mass is going to be equals to mass, which is 0.625 over number of mole, which is 5.307 exponential minus 4. So the molecular mass is going to be equal to 0.69. Let me write it down. That will give us 0.69 in gram. That is the molecular mass. But we are not solving for molecular mass. The question says we should solve for relative molecular mass. Relative molecular mass has no unit, and in that case, the value is going to be 1177.69 without unit. If it is molecular mass, it's going to have unit of gram. We have discussed that under more concept and Avogadro's number in our other videos, so you can check for it to get the difference between molecular mass and molar mass and relative molecular mass as well. So let's look at another question related to Victor Meyer's experiment. Now let's look at the second example that we can see on the screen here. The question says, in a Victor Meyer's experiment, 0.52 gram of an organic liquid of molar mass 120 gram per mole was vaporized at a temperature of 298 Kelvin and pressure of 1.013 exponential 5 Newton per meter square or Pascal. Calculate the volume, and here was a condition for us to express the volume, which is in centimeter cube of air. that is displaced. Given that the SVP, that is the saturated vapor pressure of water at 298 Kelvin to be 2.32 exponential minus 3 Newton per meter square. The first thing is to write our parameters that we are given. We are given mass of 0.52 gram. The molar mass is given as 120 gram per mole, and the temperature is given already in Kelvin as 298 in Kelvin, so no need for conversion. We are given pressure of the atmosphere to be 1.013 exponential 5 Newton per meter square, which is also known as Pascal. Then we are also given pressure of water, which is saturated vapor pressure of water, as 2.32 exponential 3 Newton per meter square. We are asked to look for the volume of the air displaced in centimeter cube. Now, what are we supposed to do? Let's try to analyze the problems before we start solving. Since we are looking for volume, that means if we try to make use of ideal gas equation, like we have said, ideal gas equation, which says that PV is equals to nRT. We can get the volume from here. Since we are given temperature, the R is a constant. We are given pressure indirectly, which is the pressure of the gas. We can get it from pressure of the atmosphere and pressure of water. So our unknown here is the volume. So that means the only missing piece is our number of mole. How are we going to get the number of mole? We can get number of mole from N equals to mass over molar mass. So once we're able to get the number of mole, we can substitute all this equation so as to get the volume. So that's the analysis of the question. So let's get started. The first thing we have to do is to solve for the pressure of the gas by saying pressure of the gas is equals to pressure of atmosphere minus pressure of water. Why? Since we are given the pressure of water. In the next example, we look at questions that is not involving the pressure of water and see how we can deal with it as well. Pressure of gas is going to be, pressure of atmosphere is given as 1.013 exponential 5 minus 2.32 exponential 3. So we solve for it. We are going to be having 9.898 exponential 4 in Newton per meter square. That is the pressure of the gas. The next thing is to solve for the number of mole. So for the number of mole using N to be equals to mass over molar mass, we are going to be having mass is given as 0.52 while the molar mass is given as 120. So the number of mole is going to be 4.33 exponential minus 3 mole. So that, since we have gotten the number of mole, then we can as well use the ideal gas equations that says from ideal gas equation, which is given as PV is equals to nRT. That's equation 2. So if we make V the sole formula, we are going to be having V to be equals to nRT over P, equation 3. So our value is going to become V is equals to, the number of mole gotten is 4.33 exponential minus 3 multiplied by R, 8.314. Why are we using 8.314? We have already said that if our pressure is in Newton per meter square and the volume is expressed in meter cube, we're going to make use of 8.314. That means temperature is 298 over our P value, which represents the pressure of the gas that we have calculated, is going to be 9.898 exponential 4. So the volume of the gas is going to be 1.084 exponential minus 4 in meter cube. Why is it meter cube? Since the R that we have used is expressed in Newton meter per mole per Kelvin, and the pressure is expressed in Newton meter square. So volume for the unit for the volume is in meter cube. But the question gave us a conditional statement that we should express the volume in centimeter cube. That means we need to convert our answer that we have gotten, which is in meter cube, we need to convert it to centimeter cube. You can check out the previous video that I did on conversion process so as to understand how we are going to do this conversion. So the first thing is that we need a conversion factor for converting from meter cube to centimeter cube. So we start with a linear dimension by saying 100 centimeter is equal to 1 meter. But this is a linear dimension which is actually meant for length, but we need cube of it, which is volume dimensions. So the next thing is to cube everything. That means 100 raised power 3 centimeter raised power 3, then we have 1 raised power 3 and m raised power 3 as well. So here we are going to be having 10 raised power 6 in centimeter cube is equals to 1 meter cube. This represents the conversion process from centimeter cube to meter cube or meter cube to centimeter cube. Now that we have obtained the conversion process, we multiply the value that we are given by the conversion factor by saying our value given is 1.084 exponential minus 4 in meter cube. We multiply it by the conversion factor, which is given as this, in a way that the unwanted unit, which is meter cube, cancelled out, and our unwanted unit, that means since meter cube is up, the meter cube here is up, that means this 1 meter cube is going to be down. I'll be writing it as 10 raised power 6 in centimeter cube over 1 meter cube. By so doing, meter cube cancel meter cube, and we are going to be left with volume as 108.4 in centimeter cube. So this is the volume of the air that was displaced in centimeter cube. So let's look at the last question here, which says in a Victor Meyer's experiment, 0.23 gram of a volatile solute displays air which measures 112 milliliter at normal temperature and pressure, which is also the same thing as standard temperature and pressure. Calculate the vapor density of the air displaced. So let's analyze it by writing out our parameters. Given data, we are given the mass of the known substance, which is 0.23 in gram, and we are given the volume of air displaced to be 112 mils, which is known as milliliter. At normal temperature, our normal temperature is also known as standard temperature is 273 in Kelvin. Then the pressure is 1 atm, or we can also say 1.013 exponential 5 Newton per meter square. So the cell should calculate the vapor density of the substance. To go about this, we are only giving pressure of the atmosphere here. We are not giving the pressure of water. So that means the pressure of gas is the same as the pressure of the atmosphere, which is given as 1 atm, or we say 1.013 exponential 5 Newton per meter square. We're also given the volume. We should take note that 1 milliliter is also known as 1 centimeter cube. So that means this 112 milliliter can also be written as 112 centimeter cube. So the next thing now is to solve for the vapor density, but let's analyze what we want to solve for. We are looking for the vapor density. That means from the beginning part, we discussed the relationship between vapor density and molecular mass, and we said it is 1/2 times molecular mass. That means if you're able to get the molecular mass of the substance, that means we can get the vapor density. So how are we going to get the molecular mass? So we are going to make use of ideal gas equation to get the molecular mass from number of mole equals to mass over molecular mass or molar mass. So if you're able to get the molar mass from here, since we are given the mass and we calculate the number of mole from ideal gas equation, then we can get the molar mass. So after obtaining the molar mass, then we can now use it to solve for the vapor density, and that's the analysis of the question. So if that be the case, let's continue. Let's convert our volume from centimeter cube to dm cube, or from centimeter cube to meter cube. We have been solving questions that involve R to be 8.314 Newton meter per mole per Kelvin. So let's try to use the R that is given as 0.0821. Now this R works with dm cube, which is also known as liter, dm cube atm per mole per Kelvin. And we have discussed that whenever we are making use of this value of R, that means our volume will be in dm cube and our pressure will be in atm. So since we have our standard temperature, our standard pressure to be in atm or unit per meter square, we are going to make use of the pressure that is in atm. Then we need to convert our volume from centimeter cube to dm cube by dividing by 1000. Why? Because 1000 centimeter cube is also known as 1 dm cube. So let's convert our volume to dm cube. That means 112 divided by 1000, and that will give us 0.112 now in dm cube. And our pressure is already in atm, so we can solve by using ideal gas equation, which says that PV is equals to nRT. Here we can use it to solve for the number of mole first. Since we don't want to solve for the number of mole, we can just go through this equation as the number of mole equals to mass over our molecular mass. So anyway we see number of mole, we replace with mass over molar mass. So our equation becomes PV is equals to mass over molecular mass and RT. Now we can make molecular mass the subject of the formula. To make molecular mass a formula, they will just switch side with PV. So our equation is going to become molecular mass is equals to mRT over PV. This is our new equation. So we can solve for the unknown by saying molecular mass is going to be equals to, our mass given is 0.23 multiplied by 0.0821. Since we are using R to be 0.0821, that means the pressure and volume will be atm, while volume will be in dm cube. So multiplied by temperature is 273, which is our standard temperature, over pressure is 1 atm, multiplied by volume, which is 0.112. So if we solve for the molecular mass, we are going to obtain value of 46 in gram. Now that I've gotten the molecular mass, the question says we should solve for the vapor density. We recall from the relation that we have proved in the beginning of the video that says vapor density is equal to 1/2 times molecular mass. In this way, the vapor density is going to be equals to 1/2 times the molecular mass we have obtained is 46. Then the vapor density becomes 23. This is the vapor density of the gas. So with this, we have looked at questions related to Victor Meyer's experiment. These other examples that we are seeing on the screen, you can try to solve them and send your solution through the comments section. There are questions under Victor Meyer's experiment. Provide solutions to them, and let's check it together to see if you are correct. So thank you.